Hello everyone. In this video, we're going to be evaluating an infinite sum, an interesting one. You've probably seen this before if you've done some calculus or if you're interested in sequences and series. And I believe Black Pen, Red Pen made a video on something similar. Not exactly the same way, but it's a different approach. It's not a different approach, I would say. It's kind of backwards. Anyways, hopefully you got what I said. Anyway, so we have this x minus 1/3 x cubed plus 1/5 x to the 5th minus 1/7 x to the 7th, so on and so forth. So basically what happens here is we have the odd powers of x, the signs alternate, plus minus, plus minus, plus minus, and we have coefficients. And the coefficients are determined by the power of x, whatever the power of x, it's the reciprocal. The coefficient of x to the whatever n is 1 over n with a negative 1 to the power something so that the signs will alternate. Obviously, you can write this using sigma with this summation notation, but that's not the point. I'm just going to leave it like this, and I want to show you a way to evaluate this sum. Does this converge? We'll find out. I'm not going to go into any of the proofs, nothing rigorous, nothing crazy, just evaluate this expression. Okay, how do we do that? So this is an infinite polynomial, in other words, a series expansion. And I'm hoping that this is a series expansion for some well-known function. So we're going to find out. All right, so let's go ahead and start by setting this equal to f of x. So that's our infinite polynomial, or our power series. How about that? We can call it power series. So in this power series, here's what we're going to do. We're going to do a little bit of calculus. Obviously, this is differentiable, right? Hopefully. Well, at least as far as we can see, it's an infinite polynomial, so hopefully it should be differentiable. And then we're going to differentiate it. But what happens when we differentiate it? It becomes something nicer. And then we're going to go back and reverse the process and get something more meaningful. Okay, anyways, let's differentiate f with respect to x. The derivative of x is 1, the derivative of 1/3 x cubed. The derivative of x cubed is 3x squared multiplied by 1/3. It's just going to be x squared. And the derivative of x to the 5th is x to the 5x to the 4th, but the 5 and the 1/5 are going to cancel out, and we're going to get x to the 4th. And then the derivative of x to the 7th is 7x to the 6th, but the 1/7 and the 7 are going to cancel out. You're going to end up with minus x to the power 6, and then you're going to get plus x to the 8th, so on and so forth. You get the idea? So by differentiating this function, and I apologize for the noises, I guess it's a plane. Anyways, I don't know if you can hear it. But when we differentiate this function, we get even powers of x, and the coefficients are 1 or -1, so it's much, much nicer. And guess what? This is an infinite geometric series. And we do know how to evaluate it as long as x is on a certain interval. Make sense? Okay, great. Let's go ahead and do this. So first of all, to make it more geometric series looking, I want to write it like this. Negative x squared, and then negative x squared squared, and then negative x squared to the 3rd power, so on and so forth. In a geometric series, our terms or sum looks like 1 plus r squared plus r cubed, dot, dot, dot. And this is exactly what it looks like. So r is the common ratio, which is negative x squared. Make sense? And what is this sum equal to if r is between -1 and 1? So we basically want negative x squared to be between -1 and 1. We don't want the equality. We only want strict inequality. Okay? And from here, basically, you can solve for different scenarios. Like, for example, if you solve this, it's going to give you x squared plus 1 is greater than 0, which is always true. If you solve this, that means x squared minus 1 is less than 0. That just means x is between -1 and 1. Make sense? Okay. So let's go ahead and work this out using our formula. Our formula tells us in the case of infinite geometric series, the sum is evaluated as 1 over 1 minus r. Awesome. Then we know r, so we can go ahead and evaluate our geometric series. So let's go ahead and do that by using the formula 1 over 1 minus r. but our r is minus x squared, therefore is going to turn into a positive expression. Okay, so what is this? This is f prime. Okay, but this is f prime. So great. So we differentiated our geometric series and we got f prime equals 1 over 1 plus x squared. Great. So what can I do with this? Lots of things. You can integrate to go back to f of x, and that's the goal, right? We're trying to evaluate f of x, remember? And we can go ahead and write it like this. The derivative of f prime can, be written as, or we can do the following. We can multiply both sides by dx, and then integrate both sides, right? And when you integrate f prime x, you get f of x with a constant, but I'm going to put that constant on the right-hand side. What is the integral of 1 over 1 plus x squared? You can try the substitution trigonometric sub, x equals tangent theta, blah, blah, blah. But you should know this as a formula. Even when you're doing the junior calculus, you should know that this is tan inverse of x. And of course, I want to include a constant c here. So this is the derivative of 1 over 1 plus x squared is the derivative of inverse tangent function. If you don't know that, you can go ahead and use this substitution. But I'm going to keep it at this. And now let's go ahead and evaluate, or is that the answer? Well, we still have to, and let me kind of quickly tell you, okay, fine. I'm just going to quickly tell you how to proceed with the substitution, but now finish it up. So dx is going to be secant squared theta, d theta from here. And then 1 plus x squared is 1 plus tangent squared. That is going to be secant squared as well. Now this is going to be turning into a very, very nice integral. If you look at it, replace dx with secant squared theta, d theta, and replace 1 plus x squared with secant squared theta. And guess what? You get d theta, which is theta, and so on and so forth. The rest is fairly straightforward. Make sense? Great. So let's go ahead and I'm also going to show you a graph, which is really, really cool, I think. But anyways, let's go ahead and find out what c is. How do I find c? So f of x is this huge sum, right? So x minus 1 over 3x cubed plus 1 over 5x to the 5th minus 1 over 7x to the 7th plus dot, dot, dot is equal to tan inverse x plus c. So here's the deal. Replace x with 0 on both sides. Don't use 1 or something else. You're going to run into some trouble. Obviously, you can use 1 as well. That's going to give you something else. 1 minus 1/3 plus 1/5. This is beautiful. Anyways, let's not get distracted and replace x with 0 on both sides. So I'm evaluating f of 0, which is 0 on the left-hand side because everything has an x in it. So it's 0 totally. And tan inverse of 0 plus c. This is also 0. So c is 0. Everything is 0. So we are all good. And let's go ahead and write the final answer. And then I'm going to show you the graph real quick. And then we'll finish up. So our series is tan inverse of x. Let's go ahead and take a look at the graph, which is really cool. I kind of gave you the part of the polynomial. So this is a finite polynomial. This is the infinite version. And as you can see, they overlap a great deal. The dotted line is for tan inverse, and the other one, the pink one, is for a partial polynomial sum. And this brings us to the end of this video. Thank you for watching. I hope you enjoyed. Please let me know. Don't forget to comment, like, and subscribe. I'll see you tomorrow with another video. Until then, be safe. Take care. I'll see you next time with another video. Be safe. Take care. And bye-bye.